Hey everyone. So last night I first wasted a bunch of time trying to get Python talking to Godot from the command line over standard IO. Godot doesn't want to read lines without from a pipe. But then I worked past that. I just made a workaround, and then I was able to get a good chunk of actually write some tests for some of these comparison or basic operations like the stack operations. That's done now. Numeric operations, bitwise operations, comparison operations. Not actually sure what those do. I have GitHub Copilot installed, and it just actually generated a bunch of them. Yeah. So it's pushing a Boolean on there. I think not sure what happened. Probably is going to crash when I do that because it's pushing it onto a typed array. Get started. But yeah, it's mostly working. So I'll write some test cases for those later. Those are minor things. The main thing I really wanted to get done are the big things, the things that read and write to memory. Actually, these are not done. So the things that read and write to memory and do the control flow. So I'm going to start with control flow ops. And what we have here, some of these I'm probably going to get rid of, like even greater than and greater than or equal to. Probably you don't need those because you can just put the arguments on the stack in the other order, and you can also negate the answer. So I think those are probably going to go away. I might even put a kill list on here to things to remove. Probably greater than and greater than equal. Just swap arguments. The idea is there's only like slots for 32 instructions, and I think it makes sense to put the most powerful things on there, even if that means getting rid of something that you would expect, you might naively expect to be there. Not equal. I don't know, like that's probably useful more often than, it probably ought to be one instruction, but we'll see. I also have jumps, and I kind of suspect that jumps are not really all that necessary. Like maybe there's a better thing that we could do, which would be like a tail call, which is like jump to the address that's on the top of the call stack, as if you would recursively cursed into the thing, and so then you could push something on. So if you really needed to do a jump that was very far, you could make that happen. But most of the time, the jumps that you're doing are going to be very short. So a call is something that goes to something far away in the code, but the jumps could be relatively short. And so the idea is that there's some you could have a difference between whether you jump by an absolute amount to an absolute address. That might go away, and replace it instead with a hop. So the hop would take a byte rather than 4 bytes, 4-byte integer. And that way, actually, it would take a signed byte, so you could hop forward or backwards, and call that a short, or they called it short in Pascal, where I learned to program. And the idea would be, you free up 2 opcos because you don't have jump at 0 and hop at 0, but you could maybe add one for tail calls and one for tail call of 0. That would still give you the jump, and you could still achieve a long jump, but I don't expect to be writing or generating that kind of code, right? I expect to be the longest jumps that I expect to do would be like calls, a call to a function and then return later. So I think call kind of covers everything. Yeah. I also have I've spec'd out an operation called eval that like takes, you give it an address and then it calls that address dynamically. And maybe that makes sense. I don't know. So that will allow you to do like table-driven control flow and that kind of. Yeah. And I was thinking about making some like more complicated instructions. So the memory instructions are also kind of dual like that. You've got a read byte, read a short. So because the stack is 32-bit, each item, each register in the stack is a 32-bit register signed. And so the question is, if you read a byte, do you want that byte to be a negative number or not? And so there would be a read byte and read short. But I don't know. I mean, that could be, if I don't need that, then maybe that's an operation I could do elsewhere. So a short is between negative 128 and positive 120. And rather than 0 to 255. So anyway, then we have write byte. If you write a byte, it doesn't matter whether it's signed or not. It's just a byte. Read integer, write integer, 32 bits. And then these were, I think there actually should have been like 3 of them. So we have these registers. You have named registers. And I was using 3 of them, X, Y, and Z. My plan was to use them for copying arrays. And I haven't actually gotten to that point where I'm implementing any kind of array copying here. But the idea is you would have something that would have a pointer to memory, and then you could read from that pointer and increment it all in one operation. And I think that's what these are going to do. But you might also want to do that without the increment. So I don't know. I'm not really sure. So I have these special, and I've never used them yet in anything yet. So I kind of reserved them, and maybe I put them as things that or remove or reconsider. That would be XY, or rather XD, DY, inc or not, increment or not, overflow flag. So where do you get a flag? How do you tell if something overflowed? We need an opt for that. And place to store. So, yeah. Okay. Anyway, so never been to this channel before. This is not meant to be like a structured talk. I'm freestyling here. Live coding and seeing what's going to happen. Where's my terminal? My terminal is in VS Code. So as of last night, I was able to, I think you have to go up here and this is the command that I run. So I have this program called Tetris. It's actually designed to test an implementation of Tetris that you would write. You write LearnTris and it tests LearnTris for you. But it talks over standard IO, except Godot wouldn't do that. So now it talks over a pipe and it runs all the tests for you. You tell it what program to run. So this is the program we're running. And we're going to tell Godot to run b4gd, or in that directory, we're going to run CLI, the command line interface, headless, and we're going to tell it to look in input.txt for the input because I wasn't able to send data over standard input. So ostensibly has a read data from standard input line, read a line from standard input. It didn't work. It works from the keyboard, but when I tried to use a pipe to do it, it would not work. So I don't know why. Here we go. All test pass. That should run a lot faster. Running a little slow. I'm not sure why it takes. But anyway, all 11 tests pass. So we're good. That was the state last night. LearnTris, I made a bunch of changes to. I'm not checking those in right now. And then I just, yeah, the way LearnTris, I made LearnTris 10 years ago for in the Learn Programming channel, and it was, it's a cool program, but it had some usability issues. Like one of the things is you fork the repository and then put your code into the repository, and I think that's silly. That's right. So input.txt, and we can just ignore that for now. And if you want to look at what that is doing, we can say b4 input.txt. you can see these are commands that are being sent to the thing. We can actually just edit that go.sh and make a copy go.sh and we'll do vm.sh. And then in the VM, we'll set that up so I can run the, where is it? H. I'll set that up so we can run it. Skip lines is for Python because Godot puts this header there. We don't need the input.txt. So now if we say vm.sh, it's just running this long command, and we see this, and now we're in our command line, and we have some kind of like meta commands. These are like debugger commands, right? So the debugger, we can ask it to query the data stack. Well, the data stack is empty. If we put like ff, now we query the data stack, and it should have ff on it, so it has the number 255 on it in binary. We can say AACCEE, and it should say face with flexible spelling rules here. Okay, that's the idea. We can add those things together with the add. And again, look at it. They've added together. We've got some new number that has overflown the bytes. So okay, you can only type a byte in at a time at the moment, I think. Oh no, okay, so you can. So if we don't like that, you can zap it. And then there's also a control stack, and we have a command called dr, which takes the top item on the rightmost item on the data stack and pushes it to the control stack. Probably should be called dc. I have some naming issues. That's actually another thing that I wanted to put on that list. I think I don't think I wrote about it. dr and rd should be a dc, and r and cd. Call stack, not return stack. So you have in most programming languages, the runtime model, like C, for example, has what's called a stack frame. So you have one stack, and it has a chunk of data called the stack frame, and it has stuff for all your arguments, and space for all your arguments, and it has space for your local variables, and it has space for the value to be returned, and the address of where you're jumping back to, right? So all that's stored on one stack. Whereas here, you have two stacks, and this kind of takes the Forth model. Forth is another programming language that I'm very much emulating here. It's kind of old and out of favor, but it's really cool. And so it has two stacks. So one of them, so it separates the control information from the data, and that means you don't have to wipe out the stack when you call. You don't have to hide the previous stack frame when you call a function. So you just keep one stack, and you basically don't need to worry about arguments. The stack becomes the arguments. The data stack becomes the arguments, whereas the control stack has all the excuse me, the information about where to go back to when you call return. So you can call it the return stack or the call stack, and I have been calling it the return stack, but I want to use R to mean registers, and then whatever currently C means a control register, so switch that to R. Something like that. Yeah. Although R also means minimize. Okay. Switch with get. Maybe get, I don't know. Okay, well, we'll see. The idea is that even though they're two-letter codes, you only have so many combinations, and sometimes word letters are more, overloaded than you'd want them to be. This is all design stuff. The hope is that in the future, this will all be like in a nice design document, and we'll have 3 implementations or multiple different implementations in different languages, and they'll all be in sync, and they'll all pass these tests, and everything will be nice and happy, and there'll be a foundation upon which to build. Okay. So we also have an IP address, which we are not yet using, because that is part of the next item, which is sequence. So kind of the flow of the talk is that you have, I mean, it's a fact that in programming, you have a machine with all these operations, and they operate on a state. So you have your foundation is basically mutable state. And then the thing that makes it a computer, the 3 things that make it a computer are you can sequence those operations. So you have a way of storing a sequence. That's where we have RAM and the instruction pointer. And then you can make those sequences loop, which is either tail calls or just recursion or jump backwards. And then you have to be able to jump forward if you want to do the other thing, which is a conditional. So conditionals involve either conditional jump forwards, and if you want to say like else, then you probably need a unconditional jump. Although you force it by pushing the state, setting the condition you want, and then doing conditional jump. I don't really know like what opcodes are optimal, so I'm going to start with, so we're starting with 2-letter words. You can always have those 2-letter words, but they could be defined in terms of other 2-letter words. That's the beauty of a fourth-like language. So rather than nailing down right away what these bytes are, we're going to treat what numbers they correspond, what actual machine instructions, what the numbers look like in the machine. I'm keeping it very symbolic for the moment, and it's just based on the string. Then you'll jump to a particular thing, right? At some point, I do need to like assign a number, and right now they're just alphabetized, but that's probably not ideal, right? Yeah, the ideal thing is that you're going to have a library of these things, and then some can be defined in terms of others. And I think that's the main thing I want to get across. Right. Yeah, I don't know. And this also is intended to be in a kind of a sea of lots of these little virtual machines, and some of them can have be configured differently. Some of them have different opcodes. I'm not really sure how to handle that. That's about performance in different environments and meeting the hardware that you have. But if you keep it at the word level, then everything's good. Okay, so anyway, all that rambling was about what? Talking about just where I'm at right now, and let's see. I've demonstrated what we've got here. We're going to quit. Part of the reason I'm doing this in Godot is so that the students can build this little thing, and they have this as their own command line interpreter, but they'll also be able to run the Godot interface. There'll be a nice, beautiful interface on it that like shows them the RAM and shows them a screen or whatever what I'm building up to. Okay, so anyway, the tests all pass. So not what I wanted. All right. Okay. Oh, it's a little longer. It takes a little longer than I think it should be. Okay, so now the goal for today is to 21 minutes in. The goal is to talk about implementing these. Okay. Well, okay, so these can actually go into this document. So the tests are written in this little language here, and this will eventually contain some like narrative and instructions. Okay, so let's call this new section, and we're going to call this flow ops. Let's look at the list and copy this list here. I have a jump, and this is on a remote machine. Okay. And I have two implementations of this. The Pascal version is kind of the most advanced version right now. So one is in J, one is in Pascal. J, I wrote an assembler targeting it. They should be the same. I thought they weren't the same. They're close. So I did not implement hop, but I implemented J. Oh. Hop is it. Interesting. Does the BIOS Emacs before BIOS? Question on my mind is, does the BIOS actually use that? So I wrote a BIOS, or I have a start on a BIOS that it basically gives you a command line where you can input letters and then, or input words, and it runs those words. I don't think it actually, it must. Loop. UB4A is the assembler. Oh. And if it has a dot in front of it, then it's going to do this. So what do we do with if? Right, if does nothing but like A0. So it is emitting jumps. All right, well, I'll implement it the Pascal way, and then the plan will be to get rid of this. I think the idea is to make it smaller. I'd rather make it smaller. So what about here? So B3A is the assembler. Oh, B4 and then B3A, and then B3A. This is actually generated code. Let's say A0. H0. Yeah, so the assembler the self-hosting assembler generates these HP and right. So I have one version generating using hops and one version using jumps. I don't need both, and I think hop is the better way to go. Whatever. These are one-line instructions. I don't need to like think about this. I'll just implement both, and then at some point I'll probably delete hops versus jumps. I think I already said that on. Move JM and J0 in favor H, E, and H0. Okay. All right, so right, so the decision I made is I'm going to implement both for now, because I want to be able to run both the code from both of those machines, and then I'll consolidate later. All right, so okay, so all of these ops though take an argument, and the question is, what do I do in the assembler? And I think the answer is that we don't put those in the assembler. Rather, wait, this is not an assembler, this is a debugger. The assembler reads the opcodes and writes them as numbers into memory, or as some formats, symbols. So okay, all right. So no, we're not going to do flow ops first. The more logical way of approaching it would be to define sequences with debugger. All right, so define new words via the debugger. Then, once we define new words with the debugger, then step through those words. Sequences. Okay, step through those words. Then we'll add then we have to add loops and conditions, but it makes sense to introduce conditions first, because otherwise you're going to get loops that go on forever. You can't introduce loops without conditions unless you only want infinite loops. Although you have a debugger, so you can just watch it happen. Actually, maybe that motivates the reason for wanting conditions. That gives you like a solid reason. I mean, you want conditions anyway, but solid reason to want conditions. So loops, introduce loops. I'm trying to think how I can test that. Like, is there a way to prove that the test is going to time out? Because the test runner can check for a timeout, and it does terminate if you terminate your program if it takes more than like 2 seconds. I'm not sure what the test would be. Maybe just demonstrate that no matter how many, every time you step through it, you're always alternating and it's never going to end. You can see that, right? Then, so let's introduce conditions. Oh, okay. Or we could introduce we could introduce that as a as an infinite loop with a tail call, an unoptimized tail call that causes the program to crash, but because there's your control stack overload. But again, I'm not sure how like you don't want the test to like evilly destroy your to attack your system, but maybe you do. I don't know. I'll think about that. I'm not really sure. I shouldn't be thinking about pedagogy right now, like how to present it. I should just only be thinking about like what needs to be there. Right. So in that case, we'll do test tail call, test control overflow. No, not control. Call stack overflow. Call stack overflow. Growth to introduce tail calls. Oops. Now you've got a looping construct, but then other looping constructs. Explicit jump. Or explicit hop, and explicit jump and hop. Explicit jump, hop, and conditional. Or really explicit jump hop with condition. I don't mean to say words. Just jump hop and jump hop with condition. And that's for introducing loops inside of your. Okay. So define sequences in the debugger. How do you actually do that, though? So, in other words, you're not reading from a file. We want to be able to just write directly sequences to RAM. So we want to like write. So the syntax would be something like at the start of a line, we're going to say like what? Like we want to define a word, right? We're going to define a word, and it has to be in a, so it starts with a dot. In the J version, I have this word called BW, which is a silly word, and it really needs to begins word and go. But what we really want is at compile time, no, this doesn't have. Does this have to be an opcode or anything? I think we say we use this. Say A. And this is going to be a definition of A. Right? Perhaps I should draw this. We have B4, and here we have B4, B4 background. Okay? RAM layout. So we should draw it like this. So we have control codes are @ A and for each one of those we're going to say F3 over, first of all upcase all that, and for each one of these we're going to say make it bigger. Okay. And so these are the first ASCII control codes. So this is 00, 01, 02, 03, 04, 05, 06, 07, 08, 09, 0A, AB, or 0B, 0C, 0D, 0E, 0F. And C, and then I want it in caret notation. So then once we get to the next, after the alphabet is exhausted, we have these. Right? And these correspond to things you can actually press on your keyboard. So this is control, and this number on your, or this symbol on your keyboard actually produces these letters as the message going to the system. Right? And then way down here we have number. We have this. That's the last. This is going to be the last letter. So really, this should be a table. Starting at the 0, I'm going to say yep, name here. That'll work. Okay. So this is the notation for each one of these bytes. And then now you get the space. So that is like this. Then you have ASCII table. Then you go across the top of your keyboard. Surely I have this somewhere. This is important because I'm not wasting time here. This is important because this is the syntax of the debugger, the syntax of the assembler, right? So because when you want to write these bytes, you're able to do that this way. First, you actually will type an apostrophe and then quote the character. So it's a single quote of and then the character. So quote space gives you a space. Quote exclamation point, exclamation point. And yeah, now we're going across the keyboard. Because we've already used that one. One that's on 6 key. It's on my 6 key. So I'm just gonna have to watch this. I could generate this table, and I have generated this table. Where did I generate this table? I generated it under, it's under D4 ref. Whatever. I could, maybe I don't have. I know I have this one. Whatever. There's only so many of them. So okay, so we have comma, star, or asterisk, plus, comma, minus, dot, forward, 0, 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, semicolon, less than, equal, greater than, question mark, at, and then we say, then we can copy this one. For each one of these, we just say 3. Oh, didn't work. 3. And we do the same thing I did before. P, Q, R, S, T, U, V, W, X, Y, Z. Keep going. Oh, and then underscore, and then lowercase. Even watch me build an ASCII table. And then all those are lower are uppercase, and then C, and then that's what we want. And then again, we say, actually, we'll do it like this. We'll just say, oh, yeah. The pipe character might be some trouble. All right, and then once we get to the letter O, A, we got to break the line. Okay, R, we break. See if that works. Something's wrong. It'd be like that. I have letter twice or something. This is right. This was right. P, Q, R, S, T, U, V, W, X, Y, Z. Wrong. Something's wrong. They should line up. I expect these to line up. The double, this quote is not, it came from the wrong place. Where's the single quote? Up here. All right, so I had an extra single quote. Oh, good. Gotta make sure. Can't press enter on that if you. Then all the way to the end. That's it. And then this one has a special code. So that's the ASCII table. I lost them. Ah, screwed it up. And then here, these would be, all right, so you could write this like O, and this would be 1, 2, this is 3, 4. I think I can do this with the macro. 6, right, because it only goes up to 7. 2 is wrong. 2, 3, 4, 5, 6, and 7 underscore. All right, so the idea being that nope. What I'm going to do here is leave this blank and then put underscore 0, underscore 1, underscore 2, underscore 3, underscore 4, underscore 5, 6, underscore 7, underscore 8, underscore 9, or A, or B, C, underscore D, underscore E, and underscore F. So we have three little sections. And then we get to things that are not ASCII characters. That's 8 underscore. The idea was things like 80 and subtract and mul and all these things are going to go down here. Opcodes go here. Divide and so on. But I don't know how they go. Right? Why would that happen? But what I do know is that there are, how do I say this? The bottom part will be filled with opcodes, but some rows, but characters that start valid UTF-8 sequences will not be opcodes. Will not be opcodes, and all other will be in fact, in theory, I was going to say you could use them to push numbers on the stack, but I'm not sure if that's true or not. I think it is. I think it actually is. You can say I want to make a, so the, oh right. So the idea is that like each one of these says, well, like somewhere up here says this is going to be like an 8 byte number. I'm going to take 8 bytes to describe this number, even though it's only I don't know how many bytes. So there's like some kind of like multiplication step, and it says like how many things to read. So UTF-8 has a nice little multi-byte code. I don't have it all loaded in my head at the moment. Plan is to be able to send text in between these messages, in between these machines, and so the numbers that can start a valid UTF-8 are actually going to be used to generate that character that can be then sent over the wire, because the wire has, at least for 32-bit numbers. Maybe the entire Unicode plane won't be up for grabs, but some numbers cannot be start of a UTF-8 sequence. For example, I know the last two can't because they would make a number that's way too big, and some of these can't be because they would make a non-canonical representation. Like they could be used to make a multi-byte version of the letter G or something. It wouldn't make sense, so they're not allowed. And so I think basically these numbers can only be like the last digit, quote unquote digit, or the last byte in a UTF-8 sequence. And so if they're the first byte, they're invalid UTF-8, and so we could use them as a instructions. And I think we have like all 4 rows of these. That's why you get 32. That's why we're limited to 32 instructions, plus these 2, plus this one right here. This one I'm expecting to use for the query the flags. And these I expect to use for character handler. So as you're getting input over the wire on this thing, like another how do I say this? Another virtual machine. You have 2 of these virtual machines. One should be able to control the other, and you should be able to put them in a row and connect them in different ways, and they should be able to talk to each other and send messages back and forth, including text. So that's the plan, and I haven't really set that up yet, and I haven't really demonstrated that. But that way you're able to communicate between these things, and they're able to control each other, and it's not just one little tiny virtual machine. It's a whole fleet of virtual machines, and so you get like concurrent communicating sequential processes. That's the whole concept. But kind of like what you get with Go, that kind of control flow, channels and whatnot, but at the level of a tiny virtual. Okay, all right. So I think I'm done talking about all that. Anyway, the point of all this, what was the point of this? Was to say, I guess, that I'm trying to. All right, so these little notations are the things that you ought to be able to put in. Oh, I see. So if you see this bytecode, what that instruction does is look at a corresponding slot in memory. So there's going to be, at least for these first 16, and probably all 32, there are 32 registers that act as a dictionary. You can use them for all kinds of different things. Like the X and Y and Z are going to be used, so they're registers. But it's making me think that like some of the, like maybe there could be some kind of fancy operations that like increment these. Because like these are meant, like X is meant to be a pointer, right? Control X is meant to be a pointer, and Y is a pointer. So the idea is that you have these two that kind of like read an increment, and this one Z that kind of writes an increment, so that you can do a dyadic array operation where you're taking two arrays and zipping them, or synthesizing them, and something like adding two arrays. You're going to add array X to array Y, item wise, and then as you go through, you take one item from X, one item from Y, add them together, and then write that to Z. And so that's the idea. That's how I find it to use these particular three registers. And then the rest of them are just meant to be like a dictionary. And some of them, because of this notation, like I don't know. So the idea would be, and then this one you would never type yourself. This one is a special one that is a character handler for any ASCII character. And so when you get this as a control code, what it actually does is it runs this command, whatever this is pointing to. All of these, and then this one would do something special. That's kind of the plan. So these are control codes, and my thought is, I don't know. I mean, they could just push numbers onto the stack, right? And then they could just be literal numbers. And so if you want to put a number on the stack, you do this. No way to put a 0 on the stack, but you could put a 1 and so on the stack. And then like do something with that register. So then it's like multi-purpose, right? So then like if you want like simple integers, you could put little numbers on, like simple numbers onto the stack with no. But I also think that maybe it should just call directly. So I don't know if I want that, if the call to be 2 ops or what. I'm not really sure. Right now, what I have is if you want to put a 0 on the stack, you would say there'd be a number called load or load byte, and it would be a 2-bit sequence to put a 0 on the stack. And it would be a 1 byte 2-byte sequence to put a 0 on the stack. A 1-byte sequence to immediately call this thing. But I also had dedicated operations for doing this read from X and write from X and so on. So it could be that if you put a small number on the stack, then it would just put it on the stack, and then the next operation could be a single byte operation that says, okay, evaluate that. Which is what I had before, right? So then to call whatever's in register B, you would say B and evaluate, right? I don't know. I have some design work to do. It doesn't really matter for the kind of rambling at this point. This is like some design work that I've got to do, that I've got to nail down and like really figure out this question. Probably not the right time to be doing that live stream channel. So what my goal today should be to run, to reach parity with the Pascal version, get them all under test so that they're all working the same way. And then once they're all working the same way, I don't know. Like here in this code, I do have this thing that is a fake opcode, but it's basically some opcode that's acting as an escape for that thing. I'll have to think about this. I could definitely see the case for just pushing it directly on the stack, and then that's like, small numbers. You push them on the stack, you shift them left and right, and so on, and you could build up whatever number you want like very quickly. Or even have a command that takes 4 bytes off the stack and turns them into an integer, signed or unsigned. Of course, then that you'd be dealing with like a weird base. Like you wouldn't be writing literal numbers. You could only go up to the number 32 as your. It would be like writing in base 32. Okay, I'm just rambling. This is not productive. Okay, the goal for today then is to get these working. So let's just get them working the way Pascal does them, or the way the way I wrote them in Pascal. Okay, so, but again, we needed to be able to write them into the. Okay, that's where we're back. So we're back. The problem is, need a notation to read from memory. Right, and I think the very first thing I should do is I should be able to question. So we should be able to say at and a number in hex. And it should dump what do I want to say? Like I want like a symbol for that, like some symbol. Yeah, we already have a symbol. Okay, we already have a symbol for reading reading from a particular spot in memory. So if I want to read all of them at once, that's something that the debugger could do, and it should output this. It should output, say, 15 of them on a row, 16 of them on a row. This is how it should write the number 0. So we'll say first we have 4, now we have 8, and copy it again, we have 16. That's a fair output. 16, 0 bytes. That's what I want it to do. So first, inspect memory. I don't want the test to hard code what these things are. So I don't want to ever actually expose what the byte codes are. You should be able to reassign the bytes to whatever, however you want them. And there should probably be some subset that is guaranteed to be in there, and then others can be either defined as names or not. Okay, so first inspect memory. Be able to first inspect a chunk of memory. Okay, and if we were to run this, it's going to fail. What happened? Oh, the name is used twice. I have to give it a name. So read mem read. Right, and it doesn't know what that means. Okay, so now we say elif command starts with at. We'll say get mem command 1 1 1 2. Is that really a thing you can do? Elif command starts with we'll say put mem. What's wrong with this? This is not Python, that's what. Did it modify this line too? Why did it modify? Subscription index. Yeah, okay, it just doesn't like that. But wait, this existed before. Yeah, because we don't use this question. This generated it for me. This Copilot generated this nonsense line. And this nonsense line, this is not right. If it's hex, you generate. Thanks, Copilot. Okay, this is what I want. This should be mad because it doesn't know what getMem is. GetMem. Because it doesn't exist. And then command. So getMem. Slice. I want to remove something on the right at the trim. Strips the first parameters from the beginning. So right -1. And that right -1. And then we call that x2. And then getMem and putMem. Func getMem address int. Nope, that's not what we want. We want it to say. Nope, that's not what we want to say. We'll probably have to pass in vm.ram. vm.ram. Maybe this should be a method on the. And it's going to print a string, right? It's a string. Whereas putMem is going to put something in it. So getMem is going to return a string, and putMem, we have a VM is a B4 VM, and you pass, and then func putMem B4 VM, VM is a VM, and then address. Right, and we want the rest of the line. Actually, we don't want this here. We can have that as an individual command, but here we want it to be it has to be a full line. If command the line starts. Line starts with exclamation point, and then continue. Right. We'll handle that line, and then that's the line. Right. Whatever to do. For I in range 16, I would say adder plus 16. Reasonable except this, I want it to be s equals where s equals this, or result, say buff equals that, buff, and in that, but it's not going to be, it's going to be disassemble. And then return just one buffer. This string is capitalized, and because this is not found itself, so func dis and int string. Now we want that, what we just had there. If op is less than 32, if op is less than 0, return. If op is less than 32, return. We're going to return the control character, so plus op plus ord, no, character, op plus ord, that thing. And that should work. If op is equal to 0, return ops. Op is less than 32, return control code. If op is less than 128, we don't want that. We want to return a single quote. If op is equal to 0, return that. If op is less than that, single quote. We could do this in hex. Op equals 128. Op equals 128, return. Okay, so now we're still here, so match op 128, return question mark. What's wrong with this? What's wrong with this? What's wrong with this? Word and chat, they used to be okay. Godot gdscript word function. I'm pretty sure that used to exist. Okay, character. How about ASCII? We'll look at the word ASCII. pair. Okay. R as well. But ord. Code point. What was just string? Maybe string. Probably has a method for code point or something. Mm-hmm. Hmm. You get the opposite of it. I mean, you could do that. You could convert it to a packed byte array. Or I could just say, well, I don't need to know that number. I don't know how do because it's just I can just know that number before. Okay. Where did this come from? Another nonsense. Oh. We go. So this should work now. This should be passing. Starts with. Line 0 is equal to that. You'd expect it to like warn me about these non. Oh, what's wrong with this now? Stop. Get mem. Get mem. From packed byte array. Oh, right, because it is a packed byte array. RAM dot backfire, right? Colon backfire. And again. Get index 0 on base string. And 50. Yeah. What's wrong? Let's try it. Let's run it manually. We'll say at 100. Like that. Being called? Not print and print. Mem 256. For I in range, adder 15 is greater than or equal to ram sign. Break is what the answer should be. And it's probably that's what's happening. Going into an input. And this is going to now give me empty string for the but go is going to give me and complaining that the test is failing because the RAM is an empty array. Why did it? If I is less than 0, why is it going into an infinite loop? Didn't do an infinite loop. $256. Why is that? Did I expect? Oh, get mem shouldn't be printed out. I don't know, but it shouldn't break the test. Even at 0, it's going to be that because there's nothing in RAM at all. It shouldn't break the test. Why is it timing out? Because I never told it to quit. All 12 test pass. Okay. All right, so now we're able to put this into RAM. And now we're going to write something. Mem write. So we're going to put so we're at that, we're going to say put some value. So we'll put we'll put 0, 0, and we would expect to see this. And so we need to say write byte. Write byte. And this is going to fail and tell me it doesn't know what WB means. We have to define that operation. WB means. So then we say WB. So A equals dpop. That's correct. But instead of that, oh no, that's actually right. So A is the address. No, RAM B equals A. What does WB mean? I just told you what it is. Did I not save it? B. Did I have a race condition and save it before it ran or something? Oh, a valid type base pack byte array. Right, so now we have to actually make the thing have some like in init, say RAM resize 124. 1K of RAM. Okay. Close. Oh, but 0 is that, so 0 never shows that. So we say 1. And we should see control A. Probably what we really want also is now that we can write a byte, now we could probably read the byte. Right. So then right. Actually, right. Yeah, so we also want read byte, right? So say do. We have dupe already? I think we do. So dupe. And then read byte, and then show me the data stack. And it should be O1. Should be the number 1. And then quit. What does RB mean? Well, it means RB means DS push back RAM and probably we should put this as like read it first. So O100 or O100 read byte query the data stack. Oh, this is not that. It should be query the data stack. And then dupe read byte. Want that. And it should say zap it one. And that should print out. And then write the byte, read the byte, and then dump the stack again. Oh, because these have a little label on them. Say what it is. Yes. 14 test pack. Okay, so now we have a way to write to memory. And we know the instruction pointer happens to be there. Probably be able to set the instruction pointer to whatever we want. Well, no, because we could. I guess the trick would be to reset everything, so that you should always be able to reset it back to 100, to position 256. By resetting machine. I don't have a test for that. That should be. Right, so now, then the next thing you should be able to step through it. So like step. You know, even here we could do like step. This might even motivate the sequence, right? So we asked for the. I think actually I'm looking for the IP already. IP, right? No. Print the instruction pointer. We won't even introduce the instruction pointer until down here, and then we'll say step through sequence. So print the instruction pointer. That's already done. Already at the start. Starts at 100 at 56 because of we have those 64 registers. All right. So now step. We're going to tell it to step, and then we're going to query the instruction pointer again. Now the instruction pointer is going to be at 1. Step. Step and execute a no op. What does S mean? We don't know because we have VM step. What does step mean? VM step. Step. So op equals RAM IP, IP plus equals 1. Unfortunately, we're all looking at strings here, so I actually have to go into this and get that disassemble thing. So wherever we call dis, we have to say vm.dis. So this really needs to be VM after all. VM v4 VM. When we say RAM, we say vm.ram. And we say vm.ram here. And we say vm.dis. Then when we call get memory, get mem, pass in VM rather than vm.ram. Then now we can move this to find.dis, right? So now this needs to go over virtual machine. That this as a method over here. This is kind of silly. But it's this. Avoid output to a string. We're just converting it to a string and then dispatching that string. To map these to bytes and dispatch on those. Or what we could do is we could have a function. Instead of this, we could have a bunch of functions. I don't know what's faster. You have an array of functions and then just 256 of those, and then you just jump to whatever's in there. And I'm not worried about speed right now. This works. It's a little silly. Okay, so now we can move the instruction pointer, and it doesn't do anything. I'm wondering if okay, so there's a way that you could operate these machines where you just, like every character is a byte. Every byte is a has a corresponding handler, and the handler for all the characters that are printable is the one in slot 0. So the thought was that running operation 0 would be a no op. Right? But if all these other things push a number onto the stack, hmm, then I'm thinking, how do you push a 0 onto the stack? You have a 2-byte code where you quote it with a thing. So if you want to push a 1 on the stack, you push it. I don't know what's more common. I have no idea what's going to be more common. Whether it's pushing a byte onto the stack code, I would imagine that's very common. But I would also imagine calling one of your predefined, like the idea would be you would stick these addresses in your most defined dictionary, because you're not going to have a big program running on this machine. You're going to have very small programs, like one procedure, one thread, right? And so you're going to have little workers that are very, very small, and they, have their own dictionary. And so whatever 32 operations they do the most, those are going to have their own little sequences. And so that should be 1 byte code. That's kind of my thought. So I think plus then you have the actual ASCII characters could be bytecode, because you make some new virtual machine that, like, where character 0 is some parser kind of thing, like some it's a stateful reentrant parser. So every character makes, turns the gear a little bit, and it causes something to happen. And then your bytecode is actually just the text, right? So the actual ASCII characters are doing something. They're triggering the turning of the wheel of this, the gears of this machine. Kind of a weird thing, but like it's kind of neat. I don't know if people want to do that. To me, that makes a lot of sense when you're streaming, when you're sending data to the thing and you're using it as a calculator, right? That makes a lot of sense to me. But I guess you could use the same thing in the bytecode itself, right? So then you're just storing like chunks of text, and you have the interpreter and the chunks of text. So the interpreter is defined using the other commands, the other opcodes, and then if you were to inspect the thing, you would just see the source code. Kind of neat. I kind of like that a lot. So this is leading up to a decision of something that, yes, the decision is, I don't know. Yeah, I still, I've been thinking about this for a long time, and I have like a whole, like, so when you make a specification, you start like you're saying, okay, exists a universe of possible programs, or in this case, virtual machines, right? And now I'm going to put some constraints on it, and that narrows the possibility. But until you define every last little thing, you have some undefined behavior. So you're always dealing with like a a whole multiverse of things that all fit those conditions, but you haven't really specified everything yet. So there's some things that could differ, and so you have part of design, I guess. All right. So anyway, I'm stepping, and so now the point is, so now let's do 2 plus 2. Okay. So we're going to say O2, O2, I do that. Is that one of the control codes? My intent was that this, so that here you could definitely write a small number. AP mean assembly pointer? I have a thing called AP in the other file. Does that mean assembly pointer? Assembler pointer? If you're going to write an assembler, you got to say, where do you want to write it, right? I guess, like, really, we could say, like, you need a quote syntax, right? So maybe we say, instead of at that, we say at, this is where we write the whole line, right? 100. At 0, 100. And we're going to put like a bunch of things. We're going to put to the rest of the line. You could write, or we could say comma. Comma is usually what you compiler, like it compiles a number. Maybe we can put colon 100. No, because colon, we use colon. Just at 100, so we're going to write to 100, and we're going to say the next one of these things. We're going to say load byte 01, load byte, because we've never, so now you've been pushing things onto the stack, but you need a name. So this is really LB, right? So now we're introducing the idea that there are some things that you have to do. So LB 01, and then on the next line, say like AB or something like that, and load that byte, and then now we're going to step again and query the data stack, and quit, and it should say AB. Say yes, AB. That GPT is following. So LB load exactly right. LB write from memory at runtime. Runtime. We never needed it before. We never needed it. We could just, because the shell is pushing directly to the back. Just push it, because the shell we never needed it before, because our shell, debug shell, is pushing numbers directly. Okay, so I think that's going to work. So we need to translate this symbology into bytes. I mean, this is obviously going to fail. Unknown op dot dot. Where that's coming from. To comment this out. The 14 test pass, right? How is that doing? Oh, okay, so we do have unknown op somewhere. Not there. It should only be running lines that have this in front of it. Where's the dot dot coming? Unless it's disassembling something from dot dot. Oh, I know what's happening. because we have here, it says tries run this op. Right? So really, it tries to run the op, and if it doesn't fail, it says unknown op, right? So this needs to be special if command 0 equals op print. And elif run op. But invalid op is coming from unknown op is coming from step. Okay, what's wrong with that? Grouping expression. What's wrong with that? Expected closing parentheses after grouping expression. End of statement after expression found. For quick fix. What is wrong there? Not run op. Okay, I don't know. No clue why that was. I'm clearly missing something about it. Unknown op 0 at RAM. Oh, well, okay, if op equals 0, continue. But run op should just be, right? Yeah. Oh, it doesn't crash the program because it's printing the standard error, and the test runner is not looking at standard error. Okay, so that's fine. Another 2 hours into this. I feel like this is a very simple program to implement, but you have to make design decisions, and so I'm spending a lot of time on like thinking about design decisions and how things ought to be, and how I'm presenting this. I'm trying to I need to finish this and like run some people through it because I have no idea like how big of a lesson this is. 2 days worth of work for the student, or is this 20 minutes because I've made it so easy, too easy? And the idea, you're not going to be doing the design work. You're going to be given the instructions, and you're going to, kind of hopefully soak up some amount of design of this concept by osmosis, and then now you're empowered to go play with it and do your own thing. I've got a bunch of these. I haven't. Let me see where I'm at. I haven't done any kind of jump or halt or call or anything. All I'm doing so far is did do read byte and write byte. You have do nothing. I don't have halt. Halt could be written in like in code. Like the thought would be you would continue basically basically returning when the call stack is empty should be uh, halting. Should halt. But if you were to do that, you would have to know the depth of the stack. You'd have to be able to query the depth of the stack. Some of these things, it's interesting. The idea is that you ought to be able to hook up any instruction, any like object in the host language to this virtual machine. Well, the debugger is an object in the host language, so you ought to be able to have a protocol for talking to the debugger from the system, and then you should be able to inspect it. It wouldn't be a bytecode. It would just like your virtual machine could have a thing attached. Anyway, so maybe halt is not the right thing. The idea is right now, like you can't see how deep is the stack, how deep, how many things have you used. You don't know yet. And so that kind of introspection stuff is not possible. Yeah, but if you could talk to the debugger, then you could inspect yourself that way, like kind of in a roundabout way, without having to. But then, like I would think halt would be more primitive kind of thing. But even then, you need like some kind of flag that says I'm sleeping or not, because the idea is like you want to be able to inspect that on another, like on your neighbor. If you're a virtual machine, you want to be able to inspect your neighbor virtual machine to see if it's free for you to do things with, like to use as a calculator. The idea is you're going to be connected. You have a bunch of these things connected in like a grid or some kind of network, and you can always ask for help. If you need to offload something else to somebody else, you can spawn a thread. You can give it some of your code or. Right. Well, I guess we have evaluate. Like evaluate is if you can push from the data stack to the control stack, which you can, and then you return, that's evaluate. Is it? You'd have to push another return value first. You'd have to, you'd have to, I think what I just said was call a current continuation. You want to, if you want to go sub, you want to, yeah, I want this, you can have a tutorial, like build this thing, right? You go through that experience, you build it yourself. Now you got this thing, you've made it, you understand what it's going, you understand how you built it. But you don't understand necessarily all the implications of it because you haven't had time to explore it yet. So now it's like, well, okay, let's play with it in the debugger and see what we can do with this machine that we just. So it ought to be like really. Like, what's the more interesting thing? I don't know. I think when I present this, I'm gonna, you know, there's gonna be like a mix, right? You're not gonna just be building a virtual machine. You want to give people feedback like early on, right? You know, you like you want the reward of seeing it do something cool, being able to use it to do something cool, and so you need. Maybe we even gloss over some of these, you know, like some of the operations that are just like data operations, and you know, get straight to, you know, like maybe do a handful of arithmetic. Got your calculator. Now, when you want to do a conditional, let's do the comparison operation, and so on. But hang on, wait a minute. Why does this work? It should not work. This is not correct. It should not work. Just put it on. Okay. This is wrong. This has not happened yet. It has not happened yet. It should not be on the stack yet. Yet. Right? Because where the instruction pointer is looking at this, but this is executing this. Right. And then, okay, so then the question is, where is it? Well, we look at 0, 100, and we should see not AB, but we should see LB and then AB. That's what we should see. But then also 1, 2, 1, 2, 1, 2, 1, 2, and then 2 of those. Always 16 bytes. It should look like that. That's what we would expect to see. This is going to fail because this is already on the stack. So I don't know. But this is meant to prevent that from happening. Well, it says if it starts with the command, continue. It should skip over all this. It should not be executing anything. So let's write this. Let's write this and see if it print put mem. Right? That should triggered put mem. Hit commands. Starts with this. It did. Then why? Confused. I call put mem. Let me say d. Data stack is nothing. That's correct. Because it should have completely ignored that line. It's a comment. 100. Still empty. Okay, and then we d. Oh, it's failing me. I see. It's not that it put that there. That expecting that to be there, and the test is telling you that that's not there. Okay, I was. Maybe it's time to take a break here. Right, so I need to tell it to print this out. So assemble a token, a string. So S is string. Return an int. If S length, S size plus not equal to 2, print add ASM tokens should be length 2 dot, and then print error, and then return 0. Else we're not going to be able to avoid getting a actual encoding for these. We have to have a bytecode here. But the bytecode is arbitrary. You should be able to make up whatever bytecode you want for now. I'd say it's unspecified. I have not. Okay, so given a string of that, okay, so we have to deal with these. I don't believe that's a real thing. First of all, S is a string. Error is a thing. ASM token. All code pass return a value. Return 0. What's wrong with this? Size. Things don't have a size. How about length of S? And this one doesn't know what an order. ASCII buffer, but we want 1. Do that. Kind of interesting. So LB return, I guess B. Let's use the same encoding that we have in Pascal. Oh. 80, yeah, that's right. 80. Next to it. Okay, so now, but the thing doesn't actually do anything. Okay, we have the disassemble token thing, but split line, whole line. So tokes equal there. Tokes equals line split space. Tokes their pop 0. Their address equals pop 0. Write -1 hex to int. What's wrong with that? Got line 0. What's wrong with this? Parameter VM is never used. Use in a minute. Local variable address is declared but never used. Okay, that's good. Yep, that's exactly what I wanted to say. Address +1. Perfect. Thanks, little Copilot. Did I not call this one Footman? Yes, I did. Token tokes. I feel like we should be in here, right? Print. Yeah. And then print Putmin. Yeah, go on. Okay, I like that. Ah, pop does not exist. Ah, godot packed string array. I'm gonna take a break here after this. We'll just take 0. We'll just take 0. Mhm. I do wrong. But I'm lost. Okay, so we have this. So folks 0 int there poke equals poke, and we're going to put I here for I in range 1 pokes. Running slow. These tests are running slow. Invalid hexadecimal notation character in string. That's actually a problem. I saw that earlier. So you have to. We're saying that you're going to read the rest of the lines. So you have to put that on a separate line. So first, let's do this. Let's check our work. You should see that. Then I'm going to do the data, and it should be empty. Then we're going to step the data again, and it should be. Why is I didn't change any behavior. That be the same. LB not implemented yet. It is. Tell me what's wrong with LB. Oh wait, step. Hang on, step. Just say unknown op. Oh, because here. Right. OX7F. And we'll say OX80 return not dupe but LB. So we wrote LB there. But in RAM we have this question because we don't know what it is. My number's wrong here. 80 should be LB, right? 80 is LB. Putting LB at 256, yes. Putting AB at 257, that's correct. Exactly correct. when we fetched it, disassembler wrong. We put this at the memory, and then that should be at that spot. Why is it wrong? Why is it off by 1? Putting LB at 256. This should clearly be 80. This step clearly needs to be broken up into littler, smaller pieces. Okay, this is back. I'm not sure what I did to fix it, though. Now it's working. I didn't expect what I just did to fix it. But I didn't expect the bug to be there in the first place. Okay, so AB is so now we're getting this as output, and we need to change it to AB. All right, so now in the disassembler, I don't have enough space. Oh, it's in here. Some of this stuff should probably return Okay, and now load byte is not actually working. So we stepped. We don't have an unknown op here. So it should be doing something, but what? OB is not on this list, so it should. It should say it doesn't know this operation. But it didn't say that. Oh, it does. It's just way up here. I'm not going to print this on an error line because it's going to the wrong channel and I'm not seeing it at the right time. There, that makes much more sense. Right, so now that makes perfect sense. I'm just expecting it to be in line with the other stuff. All right, so ds push back RAM IP +1 and then yep, IP plus equals 1. That should work. And we should test that. RAM IP, it's already done. Yep. Now, what we need to do is move these lines here and then the test. All these other lines here. So the word pudding is here. That was a debug line. I think I'm good with that. I'll leave it. I'll get rid of it. I'll leave it. It's a complex debug line. So, and then so put mem. Right, so now this should. Okay, so we're now able to load something into memory, and I think I'm going to ask it for the instruction pointer, and that should be IP. Should be not 101 but 102 because it should have skipped over 2 bytes. If that passes, I think I'm done. Or not, maybe not for today, but for... Yep, all 16 tests pass. All right, so I'm going to cd into b4gd, git add b4vm and CLI, and git commit vm start on, what did I call this stream? Ops for on stepper and memory ops. Right now, this is at tangent storm b4-gd. There's also a b4 directory. All the other, the tests are not up yet. That's going to go somewhere else. Okay, so thanks for watching. I will come back soon, and I'm going to try and plow through this Saturday or Sunday. Saturday. So I'm hoping to get this Godot version of the virtual machine working. I've got a pretty good start now. Most of it is now that I can step through with the debugger. Inspect the IP address, or the instruction pointer, and inspect the stack and inspect the memory. Got a good start on assembling things. It is silly that I'm dispatching on strings instead of numbers, but I'll fix that later. All right. Yeah, thanks for watching, and